Hello everyone and welcome to yet another recreational programming session with Mr. Zozin. Today is another offline session, so there's no chat or anything. And today I would like to explore the inner workings of the memory a little bit. So here we have a library that we've been developing for, I think, like a month or so. It's a library that implements coroutines. I'm not going to go into the detail of what coroutines are. For now, I can say that this is basically lightweight threads. So for more information on them, you can check out this repo. It's going to be in the description. So there's a description of what coroutines are. And as any threads, they need their own stack, their own call stack, where the application is going to store the return addresses for function calls or some local variables and stuff like that. And we do allocate these kind of stacks ourselves using malloc. So we can even take a look at all of that. So it's actually, let me quickly start Emacs, and I'm going to go into the source code of the library. So it's coroutine.c, and here we literally call malloc, right? So this is basically the region of memory that is going to be used for this stack. So, and we don't really do anything particularly special with that region of memory, which kind of creates potential problems. So essentially, especially in case of a stack overflow, let's imagine that we have some sort of a region of memory, and the stack, usually on platforms such as x86-64 or ARM, it grows from right to left. It is very important. So it's not growing from left to right, it's from right to left. So that means the stack is going to be growing from here. And as you call different functions and allocate local variables and stuff like that, it is going to be growing in here. And all of the return addresses and local variables are going to be stored in this sort of region. So as soon as you stack overflow, right, so you're going to be right into the region that is beyond allocated region of memory. And it could be anything there, right? It could be like actually valid memory of some other part of the program that allocated something, and in that case it's going to corrupt that memory, and these kind of problems are very difficult to debug. So what I want you to do, I want you to actually implement it so there's a little bit of a sort of like guard region right before the stack, right? So let's actually allocate a little bit of stuff in here, and let's denote that region with some sort of a symbol. I don't know, let's replace space with X, right? And essentially that specific region of memory is going to have permissions of read, write, and execution equal to 0. So it's not going to have any permissions. So as soon as the program tries to write or read from that region of memory, it's going to segfault, which is much better than corrupting some memory. But to implement this kind of stuff, you actually have to go beyond malloc, because malloc is a standardized C function, and it's very much cross-platform, right? So it exists on Linux, it exists on Windows, it exists on Mac OS, and on different operating system, it is implemented using different API calls, right? So to be able to actually mark a certain region of memory as sort of like protected, we need to use Linux API, which kind of makes the entire library not cross-platform, but it is already not cross-platform because we have inline assembly chunks of code, which are dependent on architecture, x86-64, and on Linux ABI conventions anyway. So this library is not cross-platform anyway. So it's totally fine for us to use platform-dependent API calls anyway. So, and how we can even do all of that, how we can even mark a certain region of memory as protected. So to do that, we need to understand what is a memory page. So let's actually Google it up, memory page. Yeah, there we go. So here's the memory page. So a memory page, it's basically a fixed length contiguous block of virtual memory. Virtual memory is a very important concept in computer science, described by a single entry in a page table. It is the smallest unit of data for memory management in an operating system that uses virtual memory. Similarly, a page frame is the smallest fixed length contiguous block of physical memory into which memory pages are mapped by the operating system. And to be fair, virtual memory, it is like rather fascinating concept, right? So essentially you have a memory address, and when you're reading or writing from or to that memory address, you're not necessarily actually operating on a RAM, right? You might be operating on something else. So these memory regions or memory pages, they can be mapped to either physical memory, in that case you're operating on a RAM, or it could be mapped to file. In that case, you are reading and writing into a file, or it could be mapped to some sort of other device. It could be mapped into video memory. So in that case, you're reading and writing pixels that could be displayed on the screen, right? So it's sort of like an abstraction over the computer, right? So just because you read and write into a specific address in the memory doesn't mean you're operating on the RAM. You could be operating on anything, right? So, and the smallest unit of sort of mapping of region of memory is a page size, is a memory page. And the size of that memory page may vary depending on the hardware and the platform and stuff like that. But as far as I know, on a standard PC with Linux and stuff like that, it's going to be 4 kilobytes. In fact, you can actually check the size of the page using a call get page size. Right, so it literally returns you that. We can actually create a separate sort of like a test program where we're gonna, you know, explore all of this stuff. Memory stuff, let's call it memory stuff. I'm gonna create main.c, and I'm going to include stdio. There we go. And so what do I have to include? I'm pretty sure I have to, yeah, I just have to include uni.std. uni.std, let's do printf. Size of memory page is going to be equal to d, and get page size, like so. Let's build it, cco main.c, and let's call the program, and it is going to be exactly 4 kilobytes, as you can see, exactly 4 kilobytes. So essentially, you can, with things like mprotect, you can actually set the protection permissions for a specific page, right? So pages usually have, you know, permissions like read, write, and execute. Reading and writing is understandable. Execution is whether you can execute that region of memory, because the CPU instructions are stored in the memory, usually read and written in the memory, and whether you can execute them on the CPU, it's also a separate permission. So you can actually set that. So the idea is, let's actually allocate several pages of memory for the stack, and the first page, let's just mark it as completely protected without any read or write or anything like that. So as soon as you go to that page, it's going to sort of like segfault. So that's the plan, right? And we can use things like mmap to do this stuff. So, and I was researching how can I do all of that with mmap and stuff like that. And mmap has a lot of different arguments in here. It has flags, and flags are the most interesting argument in here because it sort of like configures the memory mapping in here. And I found a very interesting flag in here, which prompted the entire stream actually. So it is called grows down. Right, so I honestly didn't expect to encounter this flag, but it's really fascinating. So this flag is used for stacks. Right, so there's a use case for stacks in here. Well, I mean, obviously. So it indicates to the kernel virtual memory system that the mapping should be extended downward in the memory. The return address is 1 page lower than the memory area that is actually created in the process virtual address space. Touching an address in a guard page below the mapping will cause the mapping to grow by a page. This growth can be repeated until the mapping grows to within the page of the high end of the next lower mapping, at which point touching the guard page will result in a segfault. This is actually perfect. Like this is so freaking cool. Right, so essentially it will not only like grow for you automatically, but then if it can grow over another mapping, over another allocations, it will segfault for you. So it will basically automate the thing that I initially wanted to do myself manually. Right, so there's another interesting flag in here, I think called map stack, right? So map stack, I think it's just called stack. Yeah, so here's the map stack, and doesn't really do anything, but it may be used in the future kernels, right? So to indicate that this particular memory is used for the stack and stuff like that. But the most interesting one is it grows down. So, but we can just like employ that. There's nothing particularly interesting in that. It's rather quick. Just like you start using that instead of malloc, and there you go. But what I want you to do on today's stream, I want you to actually try to see if it actually does that. Right. So how can we even see that it actually grows the mapping and stuff like that? We need some sort of like a mechanism of Linux that can show us all of the existing mappings of a program, right? And in fact, there is such mechanism. It is located in a proc mechanism. Proc is a special folder, right? So /proc, and it contains information about the currently running processes. Right. So, and one of the, so if we go into that folder, right? So we have a lot of folders in here with different numbers, and those are PIDs, process IDs. So, and essentially you can go to any of this folder, right? So, and here is the information. Well, some of the things are not allowed to me, but I mean, if I was root, I could actually see all of these things. And all of these things, they contain interesting information about the current process. And one of the files that is very interesting in here, it's a maps file. Right, so, and I can't even read, maybe this entire thing does not exist anymore, right? So if the process dies, you can't really access this entire thing anymore. There is a special PID in here, which is called self. Yeah, there we go. So it points at the process of the current program. So in our case, this is a PID of Emacs, if I'm not mistaken, right? So self points at yourself. We can even confirm that, I think. Right, so I can grab this specific PID, and I can't even find that, so it doesn't exist anymore. Huh. Oh, it could be actually the PID. Oh, every time I refresh, it actually increments the PID. So that means what Emacs does, it probably calls ls, and that's the PID of ls, and it doesn't exist anymore. So it's rather fascinating, isn't it? So, but anyway, so we can even inspect our own sort of stuff and memory and stacks and stuff like that, and especially memory maps. So there is a little bit of the documentation about maps file. So it's a file containing the currently mapped memory regions and their access permissions. See mmap for the information about memory mappings, right? So, and it has this kind of stuff, which actually gives you the ranges of the addresses, permissions, some sort of offset. I'm not really sure why you need offset if you have like a specific addresses. Dev, I have no idea what that is. It's devices or something like that. And also what kind of files are mapped into that region of memory, right? So because as already said, you can map not only the physical RAM into the memory addresses, into the addresses of virtual memory, but you can map specific files. And when you operate on that region of memory, you're actually operating on that specific file. So memory is not RAM, it's more of an abstraction which may operate on RAM, but not necessarily have to. It can operate on anything, on any device. So that's basically what it is. So let's actually try to allocate some memory with grows down flag and observe how that changes mappings within the maps file of this specific thing. I think that's kind of fun. That's kind of educational. So let's actually go ahead and fucking do that. So where's my main.c? So before we can find our own maps file, I think we need to find our own PID, right? So as far as I know, there is a function literally called getPID, right? So it returns you your own PID. Okay, so PID is equal to D, and I'm gonna do getPID. Okay, so let me try to run that, and there we go. But the problem here is that we can print the path to the maps file, right? So we can do something like proc maps, and here is the path to the maps file, but it doesn't exist anymore, right? So I can just do something like file this, and as you can see, yeah, then there's no such file or directory. So one of the things we probably need to do, we probably need to wait a little bit. We can do something like get C, right? So, and just run this entire thing. So get C, I probably have to, provide the file from which I'm reading. There we go. Okay, so now I should be able to open this specific file, and here are all of the memory mappings in that specific process. So here's the interesting thing. There is quite a few mappings in here that map literally to the executable that is currently running. And there's several of them. Look at that. Some of them have permissions read-write, others have permissions read, and one of them have permission execute. My hypothesis is those things are segments, right? Because ELF executable has different segments. It has a data segment, it has a text segment, it has a BSS segment, and so on and so forth. Right, I presume that these are those, Right, I think these are those. So over here we have a mapping for the heap. It even tells us that this is the heap. There's also stack and some vvar, vvon, zulu, some stuff like that. I don't even know. I'm not a Linux person. I don't freaking know what all of that is. And other mappings are literally dynamically loaded libraries, right? So libc specifically. So if you dynamically load a library, it is actually mapped into memory like that. And I suppose the main program just jumps into the execution of all of these things. Okay, so that's pretty cool. Now, if I press enter, from compilation mode, I can't actually press enter. So I think I could do something like this. Nah, it didn't work. I probably have to put ampersand in here, and then I can press enter, and application has finished after pressing enter. Okay, so let me try to do the following thing. So let's actually try to call mmap and see what is going to happen. So here's a mmap, and it's a pretty lengthy function, I would say. It's a pretty lengthy function. So, and we probably need to store the pointer that we will get from this entire thing. So, address. What is address? Let me see. So, if address is null, then the kernel chooses the page-aligned address at which to create the mapping. Okay, this is perfect for us. So, and it's going to point at the beginning of the memory page. So, we don't even have to align anything or anything like that. It will automatically return us that. So how much do we want to allocate? Let's actually literally allocate one page, right? So let's get page size. So in terms of protection, I want to be able to read and write into the stack, right? So that means I'm going to actually set the protection into write and read, but I'm not going to enable execution for security reasons, right? So because I don't think it's a good idea. So in terms of flags, so flags are a little bit complicated, right? Because you can do a lot of things with memory mapping. For example, share memory mapping between processes. Again, virtual memory is an abstraction, so which means that kernel can actually map different virtual pages for different processes into the same memory frame of RAM, and effectively share memory between two processes. And so there is such mechanism of shared memory in Linux, which allows different processes to communicate with each other with mapped memory. So which is actually kind of cool. Maybe at some point we're going to explore this kind of mechanism. So we don't want to share this kind of memory, so we don't have to provide this flag. So I think the flag that we'll need is a private. So it's needed to create a private copy on write mapping. Updates to the mapping are not visible to other processes mapping the same file and are not carried through the underlying file. So this is exactly our case. I think we have to provide this specific thing. So there was another flag, I think anonymous, which is important for us. The mapping is not backed by any file. Again, that's exactly our case. Its content are initialized to 0. The FD argument is ignored, right? FD argument, this is a file descriptor of the file that you want to map into the memory, but we're not mapping anything, so we're going to be actually providing whatever. So that means implementation require, okay, so some implementations require FD to be -1. Okay, so let's actually put -1 just in case. Okay, so this is the second flag, and I'm going to append it in here. And on top of that, as we already said, we want to allocate this entire thing for the stack. So let's actually enable this stack flag and also say that it's going to be growing down. Right, so we enabled all of that stuff. Offset. Offset, I suppose it's an offset starting from the memory address in here, so I don't think we care about this kind of thing, so we're going to put 0 in here. Okay, so after that, as far as I know, what does it return in case of an error? In case of an error, it doesn't really return 0, even though it returns a pointer, it doesn't return 0. It returns map failed, which is actually a negative number. So to actually check for the error, you have to check for the I think map failed, right? So let's actually check for that. And fprintf std error. Error could not map memory, and let's also explain the reason. So str error no, right? And exit with this kind of thing. Okay, so we also probably want to print the pointer that we just got in here. So I'm going to put ptr in here. Okay, and I think we need to wait again, because it's like if we don't wait, it's going to exit, and the the folder with memory mappings is going to disappear. So I think we need to actually wait a little bit in here. All right, so let me try to rebuild the whole thing super quick. Okay, so we have to include, for memory map, we have to include some stuff. So let's include this thing. So main.that. What else do we want? For error no, we need probably strings, right? So it's just a string. And also for the error no, we need error no. Okay, that's cool. So now let me try to run the whole thing. Okay, here is the memory maps file. I'm opening it up. So here are all of the mappings. That's very cool. Now I'm going to press enter, and here is an address. And if I now reread the file, we got a new mapping in here, which is pretty cool. Is it, does it have the same, there we go. So we actually got a new mapping in here. So here it is. So this is literally the mapping. Let me actually double check it one more time. So here it is. So this is smaller address, this is bigger address. One of the things we can try to do, actually, we can swap them around, put 0x in here, and maybe open Python. And that's the, okay, so we allocated a single page. We actually allocated a single page. This is actually kind of cool. Right, so we can actually see all of that stuff. So does it have anything before that? Right, so if we take a look at this address and this address, there's a little bit of a space between them. Look at that. There is a little bit of a space. So that means I can take this address and then subtract this address. I just want to see how much space there is below the memory allocation that we have in here. Let me actually see. So Python, did I already close my Python? Yes, I did already close it. Python 3. So how much? Okay, so that's quite a few allocations. So let's try to see how many pages we have in there. So that's 20 pages. Okay, so there's the 20 pages, and so that means we can actually grow beyond that. Okay, that's pretty cool. Okay, that's cool, that's cool, that's cool. So now let's try to do a very dangerous thing. Let's try to do a very dangerous thing. Let's cast this pointer to the character. So all of the memory arithmetics are going to be in bytes. And let's subtract 1 byte. Let's subtract 1 byte. And then let's try to write something into that byte. So I presume after that, there should be another page created right before that one that we allocated. Hopefully, we'll see. If I understood the API correctly. So, and also let's just wait a little bit. Okay, so I'm gonna do something. Try to touch your guard page flashing. All right, so I'm gonna also put the new line in here, and let's rebuild the whole thing. And okay, so I have to kill the entire, actually, just a second. Yeah, I need to kill all of that stuff. We don't need anything in here. Cool. One more time, let's just rebuild it. Let's just run it as it is. Let's open the file. Here is our mapping. That's pretty cool. And now I go here, I press enter. So here is the address. I revert the memory mapping. The address in here is here. Okay, that's very cool. So let's confirm. So it is located in here. That's pretty cool. Now let's press enter. And it's segfaulted. It's actually not supposed to segfault. If I understood the documentation correctly. So grows down. And map grows down. Let me actually read it. So this flag is used for stacks. It indicates to the kernel virtual memory system that the mapping should extend downward in the memory. The return address is 1 page lower than memory area that is actually, okay, the return address is 1 page lower than the memory that is actually created in the process virtual address space. Touching an address in a guard page below the mapping will cause the mapping to grow by a page. This growth can be repeated until the mapping grows to within a page of the high end of the next lower mapping, at which point touching the guard page will result in a segfault signal. That is strange. Maybe there are some examples online. and how this shit is used. Let's fucking go. Okay, starting strong. All right. Okay, so what do we have here? I try to create map grows down mapping with the okay, Jesus Christ, with the expectation it will grow automatically as specified in the exactly. So I wrote the following example to test the mapping growth. Yeah, so they just like -1 page and stuff like that. Well, I mean, that is too much. You're actually skipping like, you know, below the page. But apart from that, it's pretty much the same. They even allocate a single page in here. Okay. So I know the OP has already accepted one of the answers, but unfortunately it does not explain why map grows down seems to work sometimes. So it works sometimes. Freaking Linux, I swear to God. Since this Stack Overflow question is one of the first hits in the search engine, let me add my answers for others. The documentation of map growth needs update. I swear to... Okay, so in particular, this growth can be repeated until the mapping grows to within a page of the high end of the next lower mapping, at which point touching the guard page will result in segfault signal. In reality, the kernel does not allow a map grows mapping to grow closer than stack guard gap. I have no idea what the fuck is that. Pages away from the preceding mapping. The default value is 255, but it can be overwritten on the kernel command line. Since your code does not specify any desired address for the mapping, the kernel chooses one automatically, but is quite likely to end up within 256 pages from the end of an existing mapping. Okay, there's an edit. Additionally, kernels before version 5 deny access to an address which is more than 65 kilobyte plus 256 bytes below stack pointer. See this kernel commit for details. Alright, so what does it do? Alright, so that's very interesting. Allow stack access below RSP. The current x86 pages fault handler allows stack access below the stack pointer if it is not more than these pages. Any access beyond that limit will access the segfault. The GCC fstack check option generates code to probe the stack for large stack allocations to see if the stack is... I swear to... Okay, this is not the first time that I encountered this kind of situation. There is a really weird dynamic between Linux kernel developer and glibc developer. It feels like they only communicate with each other and nobody else in the outside world. So essentially, kernel constantly introduces special hacks for glibc, and glibc always introduces special hacks for the kernel. So they exist kind of in a tandem, right? And they don't really document any of these hacks properly to anybody. They just like talk among each other, and all of that knowledge is only stored in the heads of the kernel and glibc developers. And if you're one of the developers who want to create an alternative glibc, for example, like Musel or whatever, you literally have no other choice than reading the source code of either kernel or glibc. Well, and in that case, this is open source, right? So it's kind of a fair game, but still, it's kind of like a weird dynamic. So kernel and glibc developers, they live in their own world, which is kind of understandable, right? So because nobody really goes into this weird area, which is like a contact surface between the application and the Linux kernel, right? So it's kind of like exists of its own. So it's isolated bubble of its own. So, and it kind of like a perfect environment for these kind of hacks that are undocumented and stuff like that. So essentially, I suppose if your allocation ends up in a unfavorable place, it will always segfault and it will never grow. So yeah, and it's something about like 64 kilobyte of something. What if we allocate like a huge stack that doesn't fit into this sort of like a limit, and maybe that will force the kernel to place it somewhere else where it is going to grow. or something like that. This is a really muddy thing. Like, I don't fucking know if it's gonna work or not. So we allocate in big stacks anyway, right? So in the application in here, when we do malloc, we're just allocating stack capacity, and it's like literally 20 megabytes. Can we just allocate 20 megabytes? Right, so we can try, honestly. So here's the page. Okay, so if the page is 4 kilobytes, what if we allocate, 1024 pages, which is going to be basically 4 megabytes. And let's multiply that maybe by 10. Let's allocate 40 megabytes of the stack. Right, so maybe it's going to place it in some place where it's going to grow or something. All right, so let's actually rebuild that. So where is the asynchronous and some other shites? Okay, so I think I killed it. Okay, so let's just run it. So here is the mapping. Okay, so that's pretty cool. I'm gonna press enter. That should create the mapping. I'm gonna revert the whole thing. Okay, here is the mapping. Does it correspond to anything in here? All right, so here is the mapping. It's still kind of located in the same place, so probably it's not going to work. Yeah, so it didn't really work. Is it going to allocate it always in that place? Let me actually see. So I think we want to allocate. Can we just allocate it? So like after, completely at the bottom somewhere there. I wonder if we can do that. That's a very interesting question. So all of the addresses, they kind of start with X, like 7 something something something. We can try to put 8 in there and allocate from there. So that's kind of an interesting thing. Okay, so here's the maps. So here's like roughly, oh my god, I've got an alarm clock. Ah! Wake up. Grab a brush and put a little makeup. Okay, so I apologize for that. Anyways, so what do we have? What do we have? So we have this kind of memory. So let's go back and boom. Let's revert the whole thing. It's still allocated in here. So let me save this kind of address. I'm gonna go to TMP. I think this address is kind of important. And now I'm going to go to async, and it's segfaults anyway. All right, so the idea is, what if we literally try to allocate an address which is this, right? So after all of that stuff, like what if we instruct, okay, allocate starting from here, just allocate starting from here. I think that may work, right? So just like all of that stuff aligns. I wonder if it's going to work. Okay. So let's freaking go, and I'm gonna explicitly say that this is a void star. All right, so let's fucking go. So let me open this map. That's cool. It literally fucking ignored it. So is it allowed to ignore this kind of stuff? Maybe it is allowed to ignore this kind of stuff. That's fascinating. All right, so what if I revert the whole thing? And now it's still segfaults. Fascinating. Yeah, I don't freaking know. So maybe we need to be able to do some other things. So maybe I don't rebuild it. That's kind of hard to say. But in any case, it already kind of does exactly what we want anyway. Right, so because it's basically segfaults there. So that's this. I wonder if I can... Why is it always like 7FFF? Can we just place it somewhere else? Oh, by the way, this is the stack. Right, and it allocates it below the stack. What if I wonder if it's because I provide this stack in there. So it says that it ignores in the documentation, but we know that we should not trust the documentation, right? So here, where's the mapping? Right, it says this is the stack, right? So in the allocation is kind of below the stack, so because of that, it's not going to grow. We kind of want to like allocate it after the stack in here, and I wonder if it allocates it below the stack precisely because we put this stack flag. Even though documentation says it is ignored, but we know that we should not trust documentation anyway, because these motherfuckers never updated. Right, so they don't give a shit about like the regular users. Right, I mean, they do. Right, but they probably consider this kind of area their own area, right? So, and the mere peasants like myself should not even go there and should just use malloc. You just use malloc, didn't think about it. Smarter people than you have figured it out. Go program in your JavaScript, peasant. Don't even go here. Okay? Thank you very much. So it's usually like that. That's why they never document shit. Anyways, so let's actually try to do that. And if I try to run this kind of thing, okay, so here is the mapping. Boom. So let's revert this kind of thing. And it's still located in here. It's still located in here. So that means... okay, and if I try to revert the whole... Did you see that? This motherflipping thing is modified. It actually... Wait, I need to... Wait. I need to actually repeat that. I need to... So I need to kill all of these things. Was it actually... was it literally because of the flag? Maybe that was because of the flag. Alright, so just a second. I'm gonna rewrite everything. I'm gonna rebuild everything. I have too many maps opened. Look at all of these maps files, right? So, and none of them exist. If I try to revert all of these files, they don't exist anymore because they are files of the dead processes. I hear the voices of dead processes. I read the files of dead processes. Well, let me actually rewrite it next. Okay, restart, I mean. So probe, what was that? Memory stuff. Okay. So I think this was because of that. Let me rebuild it one more time. Nah, cco main.c. Just rebuild it, please. Okay. And now I can do main, boom. Let's open this up. Let's open it up. Okay. So boom. I'm gonna copy paste this thing. I'm gonna revert this thing. Here's the mapping. We created the mapping. Let me save it. Right. Let me save it somewhere to tmp. Okay, so it was saved. Now, hopefully, if I press enter, okay, try to touch your guard page flushing. Now, observe this specific mapping, right? So let's revert this thing. And it actually went from B to A. I'm not sure if you caught that, but it went from B to A. And if we go to here, yeah, so you can clearly see that this address does not exist anymore. But if you go one page below, that's where it is. It is not growing if you provide the stack flag, but it is growing if you don't provide the stack flag, but provide grows down. Honestly, this is fucking cool. This is fucking cool. So you have a growing stack. And I suppose as soon as this memory mapping goes towards like somewhere here, right, so where it is, so it's A, if it reaches somewhere here, it will probably segfold. Right, and this is the kind of shit that you're going to be dealing with if you go slightly below libc, right? So you kind of become on your own. But some of the things are not even possible to do within libc, right? But I mean, technically we're still within libc. Yeah, we're still above libc. But anyway. Right, so I suppose, is it consistent, by the way, or did we just get lucky? So we can actually kind of test that. Yeah, I think it is consistent. I think we should just not provide the stack flag. I think that's the case. So I can try to run it several times. Yeah, so it does allow us to touch this page, but then if we put like a map stack, I'm pretty sure it will stop allowing us to touch the page. Right. No, it still allows us. So that means we got lucky. We actually got lucky. But it doesn't matter, right? So it doesn't matter. Both of the behaviors are perfect for us. So if it grows, good, right? So that means our program can run for a little bit longer. If it segfolds, good, then we can see that in the debugger. right? It doesn't really matter, right? So, and we're going to be allocating like a pretty huge stack anyway, right? So as of right now, we're allocating like 20 megabytes. So it's very unlikely that it's going to overflow on the regular programs, but if it does, I want to make sure that it guarantees to segfault, right? I don't want it to go and just touch some other memory mapping and corrupt them and stuff like that. I want my program to be memory safe. We are trying to achieve memory safety in C. Anyways, so I suppose that is basically, I think we can simply just replace our malloc with this specific mmap. So let's go ahead and do that. So we have coroutines. I already closed everything because I restarted Emacs. Where is the coroutines malloc? Let's actually do that. And so we even had to do to align the stack to 16 bytes or whatever. We don't have to do that. Memory, like mmap already aligns everything accordingly. It aligns everything by the pages. Doesn't even matter. So the stack capacity. So I don't even know. Maybe we can set the stack capacity to like literally that. So stack capacity. And the stack capacity is going to be something like this. But the problem with the stack capacity in here is that it's no longer a compile time value anymore, right? So because it just like takes the page size and whatnot. Yeah. So, and then we just do this kind of thing. But maybe that's fine. So we're not using that in a compile time context anyway, so it doesn't really matter per se. All right. So I suppose we can just go ahead and rebuild the whole thing. So yeah, let's just rebuild everything. So it wants a memory map. I forgot how to enable this kind of memory map thingy majingy. So here's the stuff. And yep. Okay, so let's actually see if our counter example still works. Well, yeah, we're still using free to deallocate that memory. So yeah, when you do coroutine finish, it tries to free all of that memory, and we're just using free in here. So if you allocated something with a mmap, you have to use mmap. Mmap. There we go. So this one. But the main difference of mmap is that it actually requires you the size, but we do know the size, so everything's fine in here. So I can provide this kind of thing in here. So here's that, and then we can say stack capacity. And by the way, yeah, we never actually check that it doesn't fail. One of the things we probably want to do in here, we kind of want to assert that this thing is not equal to map failed. Right, so that's kind of important, I think. So if it failed, you probably ran out of memory, so just buy more RAM. Just buy more RAM, just buy more RAM, just buy more RAM. And for the rest of the stuff, we're just using malloc, right? So this is just like a data structure. I don't think we need anything specific for the data structures, because they need to just store the data. All right, so let's rebuild this entire thing, and let's try to run build counter, and it seems to be working. It seems to be working. That's pretty cool. That's pretty freaking cool. So we have quite a few examples in here. Oh, by the way, I recently created like a mapping for coroutines in Jai, and they work. And furthermore, they work at compile time as well. Believe it or not. And I didn't do anything for that, by the way. Speaking of how fucking base Jai is, I didn't do anything for my C coroutine library to work at compile time in Jai. I can even demonstrate you that, but I think the problem here is that I don't have a Jai Linux. Oh, I do have Jai Linux in my path, so that means I can just do something like, let's actually build all of the examples, all of them. There we go. Right, so, and if I try to just run, look at that, look at that. So during the compilation, we did Jai Linux counter, and it actually demonstrated that coroutines work at compile time. So let's actually see. So here is the compile time block. right? And here within the compile time, it initializes coroutine library and then just starts two coroutines that are just like interleaved with each other and execute and stuff like that, and then just yields them. All of that at compile time. And again, I didn't do anything special for in the library for that to work. It just worked out of the box. It just worked out of the box. So the magic is, the magical trick that Jonathan Blow employed in here is in here. So the way you work with external libraries, you use the library sort of like a pragma or some special thing, right? And then you define foreign functions and you refer to these libraries. So here's the thing. When you define a library, you must create two versions of the library. The first one is a static library. The second one is a dynamic library, right? So, and if we take a look at this kind of thing, and we have basically static version of coroutine and dynamic version of coroutine. So what this based compiler does, it is literally loading the dynamic library at compile time and calling all of these functions at compile time from the dynamic library. Holy shit. I honestly didn't expect that it's going to do that. It's just, but it did that. Right. So you can actually confirm that, right? So you can say that don't use dynamic library, and if you try to compile this example now with Jai, so let's actually rebuild build counter Jai, it will actually tell you, it will actually explain you to you. So attempt to call a foreign procedure at compile time, but it is imported by a library directive with a no DLL option. Without a dynamic library, we don't have anything we can call at compile time. Right. So the way any library works at compile time at Jai, it literally loads the DLL. Right. So which is based. Like, I've never seen that anywhere before. That's so fucking cool. So I'm super excited for the Jai release, honestly, right? So, and it's all of that is just the tip of the iceberg. I'm telling you, all of that is just the tip of the iceberg. The whole language is filled with cool shit like that. It's just like not just a single cool idea. It's a lot of different cool ideas that are compatible with each other. It's a very much coherent thing. It's fucking cool, I'm telling you. So, and coroutines just work with this thing, right? So they work at runtime, they work at compile time, and so on and so forth. So, and also recently, right before this session, somebody submitted another cool example for coroutines with the Lexa. All right, so where essentially you run the Lexa in one coroutine, and every time you basically, formed a Lexem, a token, you just yield, and that yields to the main coroutine that organizes the loop and pulls the tokens and stuff like that. So it's also kind of cool. Like, I didn't know that you can use coroutines for that. It didn't occur to me that you can do that, but it makes a lot of sense, right? So in that case, tokenizer can be just like a single loop that doesn't care about preserving its own state somewhere, because the state is managed by the coroutines library. So the whole state is just stored on the stack, and the stacks are swapped out by the coroutines library. And I think it's actually kind of cool. Right, so let me actually see that. So here's the Lexa, right? And you're supposed to provide some mathematical expression. So let's do, I think 17 multiplied by 2 plus 35 or whatever, right? And it kind of, well, it tried. I suppose it doesn't support multiplication. Yeah, so it doesn't support multiplication. So that was the problem. We can actually add support for the multiplication. So let me actually add this kind of thing. So, and now let's rebuild everything. In any case, it's just an example, right? It doesn't have to be like a perfect or anything. Oh yeah, I forgot that I need to enable the DLL. Let's fucking go. And let's do the Lexa. I think Lexa was in the compilation, and there we go. And what I want to do is a multiplication. So, and it doesn't even support numbers, it supports only digits, but I mean, as you can see, it works, right? So there's two coroutines that are constantly sort of like switch between each other. The main coroutine that pulls the token, and the Lexa coroutine that every time it finds a token, it switches back to the main one. And that's they work sort of like cooperatively. That's probably why they're called cooperative routines. Well, coroutines are basically a shortcut for cooperative routines. I think I'm starting to understand how it works, right? So anyway, I guess that's pretty cool, right? So it's actually quite cool that you can explore literally the memory of any process, right? So you can check like memory mappings and stuff like that. And yeah, that's very useful. That's insanely useful. Right, so we just made our stack a little bit safer. A little bit safer. Any Stack Overflow is going to be at least reproducible in the debugger. So one of the things I had before is that sometimes the Stack Overflow is going to be, reproducible in the debugger, but then it will not, right? Because in the debugger, it would place it somewhere else and overflow was fine. So yeah, now with this kind of memory map call, if there is a Stack Overflow, it's always going to be reproducible because the mmap will ensure that as soon as you touch the forbidden page, you're going to get slapped in the face with a segfold. So, which is perfect. Made it a little bit more memory safe. All right. So I didn't want to make a huge session, right? Just a quick session to explore some cool thing I found. So yeah, that's it for today. Thanks everyone who's watching right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Mr. Azuz and possibly an online one. We'll see. The winner gets tea. That's for sure. I love you all. Mwah.